Hello and welcome to Topic 1, Math Skills, suitable for an algebra-based first-year chemistry or physics class. This is section 1.2, and I will be talking about how to convert scientific notation to decimal numbers. So, why do we need scientific notation? Well, scientific notation is needed to make very big numbers and very small numbers faster and easier to write. In physics, there are, 6 quintillion, 250 quadrillion. This would be the thousands place, the millions place. This would be billions. This would be trillions, quadrillions, and quintillions. So in physics, there are 6 quintillion, 250 quadrillion electrons, for example, in 1 coulomb of charge. So would you rather write out the decimal version of this number? All right, I'm just going to copy it again. So it'd be 250 followed by 15 zeros. All right, 1, 2, 3, 4, that's 2, 2, 3, 3, 4, 5, and the decimal would be there. All right. So would you rather write out that number in decimal form, or would you prefer to write out this number in scientific notation, which would be, 1 jump, 2 jumps, 3 jumps, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18 jumps. So it would be 6.25 times 10 to the 18th. All right, big number, positive exponent. This is a lot easier to write than that. Scientific notation looks like this. These are the parts of a number in scientific notation. In front of the multiplication sign, this is called the mantissa, or coefficient. Now, keep in mind that all of the numbers in the mantissa must be significant figures. We will go into the relationship between scientific notation and significant figures in a later video on significant figures. Now, you have a multiplication sign, which literally means that the mantissa, the front part, is multiplied by this, the exponent or order of magnitude. So behind the multiplication sign, you have the exponent or order of magnitude. You can think of it as 10 to the 4th or as 4 with the 10 to the understood. Now, one more thing. In correct scientific notation, there can only be one number in front of the decimal point. So you see, here's the decimal point, and there's only one number, not a 0, only one number in front of the decimal point. Let's check off the numbers which are in correct scientific notation. In other words, there's only one number in front of the decimal point. Well, here we don't even have a decimal point, so this is not correct scientific notation. Let's get rid of that. All right. If there was an implied decimal, it would be there, so there would be 2 numbers in front. So again, no good. This one, there is one number in front of the decimal point. Multiplication, exponent. This number is in correct scientific notation. Over here, all right, here's the decimal point. Only one number in front of the decimal point. Correct scientific notation. Yes. This one, well, this number has 2 numbers in front of the decimal point. That's not correct scientific notation. Now, the only time where there would not be a decimal is if there was only one significant figure. All right, so for example, something like this, if it was 6 times 10 to the negative 2, that's fine because the implied decimal would be here, and there would only be one number in front of the implied decimal point. So this would also be correct scientific notation. Remember, only one number can be in front of the decimal point. Understanding scientific notation is all about deciding whether you're dealing with a big number, in other words, 1 or greater, or a small number, numbers less than 1. If you figure out from the beginning whether you're dealing with a big number, in other words, a positive exponent, or a small number, a negative exponent, then you probably won't be making any mistakes with scientific notation. So let's convert this number and this number to decimals. All right, now what we have here is a positive exponent. Now, when the exponent is 0 or positive, you know that the number is 1 or greater. Now, since we want this number to be a big number, right, greater, 1 or greater, we're going to have to move the decimal point to the right. All right, we're going to have to move the decimal point that way. So take the 3.00 and move the decimal point 8 jumps, making the number bigger. You have to go that way. 1, 2, 3, 4, 5, 6, 7, 8. All right, so the decimal is here now. All right, and we've got. All right, now I'm not going to actually put the decimal there because we only have 3 significant figures. And again, we'll get into that later in a later video. But the number that you're dealing with, all right, what this number really is here, all right, get rid of those jumps. We got a comma there and a comma there, is 300 million. We've got 1,000 here, the thousands place here, the millions place here. This number is 300 million. Again, positive exponent, the decimal has to go that way when you change it to a decimal number. Right, now, this one here has a negative exponent. So we know that that means it is a small number, a number less than 1. So when we make this into a decimal, we're going to have to go this way. 1, 2, 3, 4, 5 jumps. Making it, we'll put the decimal here, we're making it a smaller number. Or rather, we're taking the same number and putting it in decimal form. 1, 2, 3, 4, that was 5 jumps. All right, from here, right, it was 1, 2, 3, 4, 5 jumps. Remember, we jumped that way, right? We jumped that way so that the final number is small. All right? So, again, positive exponent, move the decimal that way to get a big number. Negative exponent, move the decimal that way to get a small number. Easy, right? Now, let's see if you can recognize what some common simple numbers would be in decimal form when you see them in scientific notation. And also, let's understand that this x means to multiply. You're literally multiplying the 3 times this number. But what is 10 to the 0 power? Well, what is anything to the 0 power? Anything to the 0 power is 1. So what this really is 3 times 1. So the decimal number here would be the number 3. Now here we have 3 times 10 to the first. Well, if you multiply 3 times, what's 10 to the first power? 10 to the first power is 10. Well, 3 times 10 literally means multiply 3 times 10. You get the number 30. All right, so this becomes the decimal number 3. This becomes the decimal number 30 because it's 10 to the first power. 10 to the second power is, you know, right, 100. What's 3 times 100? 3 times 100 would be 300. All right, so really any mantissa to the second power is going to be in the hundreds. Any mantissa to the third power, all right, 3 times 1,000 would be 3,000. All right, now let's look at some other numbers that are 10 to the 0 or 10 to the first multiplied by 1, 10, 100, or 1,000. You want to be able to recognize what 10 to the 0, 10 to the 1, 10 to the 2, and 10 to the third power represent. Again, 1, 10, 100, 1,000. You really want to be able to recognize that. All right, so for example, if we had 2.53 times 10 to the 0, 2.53 times 10 to the first, 2.53 times 10 to the second, 2.53 times 10 to the third. What would they be in decimal form? Well, this is times 1, so it doesn't change because 1 is the multiplicative identity. So it's 2.53. All right, the biggest place is going to be the ones place. Here, 2.53 times 10, all right, is going to be 25.3. The biggest decimal place is the tens place. You're multiplying by 10, 2.53 times 10, literally. This is going to be hundreds, so it's going to be 253. And this one is times 1,000, so this is going to be 2,000. There's the 5, 3. Now it's 2,530. All right, and you can go on to the 4th power, the 5th power, and the 6th power. All right, those are some good decimal places and exponents to recognize at this point. All right, if you had, for example, 7.104, let's just make up a number here, times 10 to the 4th, all right, 6.205 times 10 to the 5th, all right, and let's just say 3.117, whatever, times 10 to the 6th, all right. If 10 to the 3rd was 1,000, then 10 to the 4th is 10,000. So this would be 71,000, right? It's going to be 04, all right, and that makes it 71,000. All right, remember, 10 to the 4th is in the 10,000s place. All right? Now, here, 10 to the 5th would be in the 100,000s place. So 6.205 would be 620. All right? You want this in the 100,000. 10 to the 5th is 100,000. So this would be in the 100. The biggest number you would get is in the 100,000s place. All right, and this would be million. 10 to the 6th is 1 million. So this would be 3 million something. All right, 3 million. All right, 117. Now to get this to be million, all right, and what did I really do? I took the decimal that was here and moved it 6 places. That way, it's a positive decimal. You're making the number bigger. Here's the decimal. 1 jump, 2 jumps, 3 jumps, 4 jumps, 5 jumps, 6 jumps. All right, so whether you're just thinking of it as 10 to the 6th is the millions place, all right, or you're thinking of it as 6 jumps to the right, all right, in any case, there you go, okay? So I hope you will start to recognize 10 to the 0 through 10 to the 6th for what they really are, for the numbers that they truly represent. And that will make your scientific notation to decimal conversions a lot easier and more intuitive. In the same way that we wanted the large exponents to be more intuitive, let's look at these small exponents, these exponents that are negative. All right, so this would be literally 3 times 0.1. 10 to the negative 1 is 1/10 or 0.1. So this would be 3 times 0.1, and that would be 0.3. All right, now here we have 3 times 10 to the negative 2. 10 to the negative 2 is 1/100th. Let's see what 1/100th looks like. All right, 3 times 0.01. That's 1/100th. What's that going to look like? 3 times 0.01. Now you can do this on your calculator. You can literally plug in 3 times 0.01. See what you get. You're going to get 0.03. All right, so we want these simple exponents, 10 to the negative 1, 10 to the negative 2, 10 to the negative 3, to be somewhat intuitive. You look at it and you're like, oh, I know what that is. This is 1,000th. All right, so that would be 3 times 1,000th. 0.001 is 1,000th, and that would be 0.003. All right? So again, you want to be able to recognize when it's the tenths place, 3/10, the hundredths place, 3/100ths, right? The thousandths place, 3/1000ths. All right, now if you were to do some other number over here, we'll try to make it a little bit more complicated. We'll do 2.1, we'll do 4.87, and we'll do 6.509. I mean, it doesn't really matter how many numbers we put over there. All right, so trying to make it more intuitive, all right, this is going to be the tenths place. All right, the biggest number you're going to have is in the tenths place. So this would be 0.21. All right, in other words, 2.1 times 0.1. All right, this one would be 4.87 times 0.01. All right, so that's going to be 0.04, all right, 87. All right, the biggest number that you have is in the hundredths place. All right, and here we have the thousandths place. This is 6.509 times 0.001. Literally multiply this by that, all right, and the biggest number is going to fall in the thousandths place. So that's going to be 0.006509. All right, again, tenths, hundredths, thousandths. Okay? I hope that you understand that this is literal multiplication here, this multiplication sign. The mantissa times the exponent is what we're literally doing, and you can plug it into your calculator. Right? And you'd like some of these simple exponents to become, wow, I know that. I don't even have to think about it or think about jumping the decimal. I know exactly what number that should be. So let's see if you can convert these real fast. Okay? So 10 to the second is 100. So 7 times 100 would be 700. Okay? 10 to the third is 1,000. So this would be in the thousands. So it would be 2,340. Right? It has to be in the thousands. Right here, 10 to the 0 is 1. So it's just going to be 6.4. All right? The biggest number is to the ones place. Here, 10 to the 6th is million. So this is going to be have to be 1.5 million. All right? 1,000,000. All right? 500,000. All right? The 1 is in the millions place. Okay? Now let's just try a few negative exponents. Now you're going to finish the rest of the examples on the worksheet. I did the first couple for you. All right? The first 4. All right? Let's do the first, maybe the first 2 negative exponents. We've got here 3.4 times 10 to the negative 1. And let's do 6.455. We'll do that one times 10 to the negative 3. We'll do 2 of these. Okay? So here you see that this is going to be to the tenths place. Remember, it's with a th at the end, the tenths place. All right, so this is going to be 0.34. All right, the biggest number is to the tenths place. And this, 10 to the negative 3, is the thousandths. Thousandths. There's a th at the end. Thousandths. Thousandths. Th. All right, so to be to the thousandths place, it's going to be, let's see, that's the tenths place, the hundredths place. There's the thousandths place, and there's the 455. So here is this number in decimal form. Again, I hope by practicing on this worksheet that these simple conversions become very, very, like second nature, very, very intuitive. Now let's look for some very big numbers and some very small numbers on your physics reference tables. Now, very big numbers are recognized by their positive exponent. A very big number, a number 1 or greater, is going to have a positive exponent. And a very small number, right over here, is going to have, that would be a number less than 1, is going to have a negative exponent. A very small number would have a negative exponent. All right, so we look on the front page of the reference tables, and all of these numbers have names. So the name is on the left side, and the number is on the right side. The speed of light is a big number. Speed of light in a vacuum is 3.00 times 10 to the 8th. All right, so 3.00 times 10 to the 8th, and the unit is meters per second. Don't forget to put the unit. Now the mass of the moon is 7.35 times 10 to the 22nd kilograms. Remember, these numbers are on the front of your reference tables. You'll also find numbers with exponents on page 2 and page 4, maybe some of the other pages, but mostly pages 1, 2, and 4. All right, the mass of the moon was 7.35 times 10 to the 22nd. All right, 7.35 times 10 to the 22nd, and the unit is kilogram. All right, so converting these to decimal form, we know that a positive exponent should be a big number, so the decimal point should be going that way. So it's going to be 3 and 8 jumps. 1, 2, all right? 1, 2, then 3, 4, 5, 6, 7, 8 jumps, which puts the decimal over there. So this would be the speed of light converted from scientific notation to decimal form. The mass of the moon, 7.35 times 10 to the 22nd, a very big number, a positive exponent. All right, 7.35, and we're going to jump 22 jumps that way. So we've got a jump, and then another jump. That's 1, 2, 3 jumps, 4 jumps, 5 jumps, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. I'm running out of space here. Okay. 1, 2, 3, put a comma. 1, 2, 3, put a comma. 1, 2, 3, put a comma. 1, 2, 3, put a comma, put a comma, put a comma. All right, so what do we have here? Comma here. Okay, that looks like, let's see. We've got the thousands place, millions, billions, trillions, quadrillions, quintillions, 73 sextillion, 500 quintillion. In any case, a big, 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 big decimal number. And again, you don't want to have to write out these big decimal numbers. That's why we're teaching you scientific notation. Okay, so very big numbers get a positive exponent, and very small, well, we haven't done the very small numbers. Let's do those now. Now we're going to look up 2 very small numbers on your reference tables. The first one, the rest mass of an electron, is on the front page, and it happens to be 9.11 times 10 to the negative 31 kilograms. All right, so it is 9.11 times 10 to the negative 31 kilograms. Then we're looking for the resistivity of copper at 20 degrees Celsius. For that, you turn to page 4. And there's a chart, and here's the resistivity of copper, 1.72. 1.72 times 10 to the negative 8, and the unit is ohms times meters. That's ohm meters. Now, it's not ohms per meter. It's ohms times meter. So don't write ohms per meter and don't say ohms per meter. It's ohm meter. Okay, so now we want to convert these to decimal form. Now, these are both negative exponents. They're going to be very small numbers. All right, so I'll put the 9.11 here. All right, and we're going to start moving the decimal that way to make a small decimal number. So we've got 1, got to go up to 31. That's 1 jump, 2 jumps, 3 jumps, 4 jumps, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31. So there's the decimal point. Okay, this would be the mass of an electron in decimal form. That's an awful lot of zeros. I don't ever want to have to write that on a test or do that in a math problem. I would rather just use the scientific notation. All right, now here, the resistivity of copper, 1.72 times 10 to the negative 8. We've got 1, 2, 3, 4, 5, 6, 7, 8. So we've got 1, 2, 3, 4, 5, 6, 7 zeros, and the decimal was there. So here's that number in decimal form. Not quite as many zeros as the rest mass of the electron, but more zeros than I care to be writing. All right? So what we have here are small numbers, all right, which we found on the reference tables, the physics reference tables, and we've converted them to decimal form, but I think I'd rather use them in scientific notation. Wouldn't you? To complete the next page in your worksheets, please make sure you've downloaded the physics reference tables. It's 6 pages. It would be nice if you printed them out. It's much more handy. Or just put it on your desktop. Download them from nysregents.org. And what I'd like you to do is look up the numbers in the next 7 problems, right, and convert them to decimal form. At this point, you might already know what you're doing. You might just get it. You probably don't even need rules. Right? But if you ever get stuck, look at these rules. Steps to convert scientific notation to decimal numbers. Step 1, you look at the exponent. If the exponent is 0 or positive, it's going to be a big number, 1 or greater. If the exponent is negative, it's going to be a small number, a number less than 1. Step 2, if the exponent is 0, in other words 10 to the 0, just get rid of it. You're multiplying by 1, so you're not changing that decimal number in the Mantissa. If the exponent is positive, you're going to move the decimal to the right to make a big number. If the exponent is negative, you're going to move the decimal to the left to make a small number. And in both cases, you're moving the decimal the same number of jumps as the exponent. So again, you probably get this already, but if you ever get stuck, just look at these rules again. Let's practice the rules with these numbers, and then you can finish the rest on that page in the worksheet. Okay, so negative exponent, the decimal is going to go that way 1 jump. So 1 jump, it's going to be 0.302. Okay? Positive exponent, it's going to be a big number. The decimal has to go that way. 14 jumps. 6.44, so we've got 2 jumps. All right, that's 2 jumps. And then 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 jumps. All right, so we would put a comma there, and a comma there, and a comma there, and a comma there. Okay, so that would be that number in decimal form. Over here, 10 to the 0 is 1. 8.0 times 1 is just going to be 8.0. Right now, it doesn't really matter whether you put 8 or 8.0. When we do the video on significant figures, you will understand that these 2 numbers are both significant. That's why they're in the Mantissa. So this is showing that both the 8 and the 0 are significant. Don't worry about it for now. If you put 8 or 8.0 for now, it'll be okay. Unless your teacher already taught you significant figures, in which case 8.0 is correct. All right, here, times 10 to the 7th, a positive exponent. All right, so you're going to go that way. All right, the decimal is going to jump that way. All right, so 4.48. So it's going to be 1 jump, 2 jumps, 3, 4, 5, 6, 7 jumps. And here is the number, the decimal number, when you're finished jumping. All right, so please finish the examples on the worksheet page that are similar to these. If you have any problems, go back to the rules. Read the rules again, okay? If it's easy, just do it. Just a word about significant figures. It's coming up in a video very shortly, right? But just quickly right now. All right, if I write 120 without the decimal point, then these two numbers are significant. You've got two significant figures. I'm going to put 2 sig figs. When you put the decimal point, you're telling everybody that this 0 is also significant. So here you have 3 significant figures. Now this rule actually goes like this. If you see a decimal point, then all the zeros after the last non-zero are significant. So the last non-zero is 2. Right, so all the zeros after the last non-zero are significant. Again, if you see a decimal. Well, I do see a decimal. So all the zeros after the last non-zero are significant. Let's try one more. All right, 3,400. All right, 3,400 without the decimal. These two numbers are significant. That's 2 sig figs. Okay, if you put a decimal, all right, let's say it looks like this. All right, now, since you see a decimal, all the zeros after the last non-zero are significant. So this number has 1, 2, 3, 4, 5 significant figures. And again, let's not worry about it too much right now. We've got a couple of videos on significant figures which you're going to want to watch. But just in case your teacher has already shown you significant figures, then you should probably be applying it at this time. If not, it's like one of the next videos. Just look up significant figures. There's 2 or 3 videos on significant figures coming up.